and see first what are the grading guidelines for this video presentation. So I have kind of grouped these into three categories as per the guideline: the use case, and all these there are 9 points, and each carries 1 point. So total will be 9 points, which I would try to address here. The first one is use case, and then second is the data set. The third is data quality assessment about the data which has been chosen here. Then we will go for data exploration, like we will try to understand data discovery. Then next would be data visualization, and third would be feature engineering. So after that, feature engineering, like missing value imputations and other techniques like that, of and like finding correlations and all this kind of data transformations, feature engineering. Next we will move for model uh, uh, creation and justify the model performance. So we will choose the scores. So I have chosen some root mean square, RMLSC, and other metric which I will share. And the two models has been taken. One is machine learning, which is a random forest in particular, and another is deep learning model, which is in particular neural network model actually with back propagation. And third is that what has been feature engineering and how the model has been created, all these documentations. So let's get started. So this is the table of contents, like agenda. As I mentioned, three parts and the two models in the third part. So to start with, business problem, use case, and data understanding. So I have taken capital bikes here, and the capital bikes here was a project competition held on Kaggle some 5 years back. So the left screenshot is actually taken from the Kaggle, and actually capital bikes here is a bike share riding app which is started in 2010, and they have been making their data available publicly. So for this particular project, 2011-2012 data is available. I've shared the link here on Kaggle, and also where the large repo of the data is available for various years, almost for 10 years now, since the data has been being captured since 2010. So it's 2020. They have been capturing and making this available for academics and researchers, and even those who are interested into data scientists. And the business objective is to forecast or predict the rental demand in Washington DC area. So we have narrowed down the data for a particular Washington DC area, and as per my understanding, the data has been taken from Washington DC central metro region. So there are two files provided. One is hourly data and one is daily data. So the data varies from September 2011 till August 2012, and the data has been there for 21 days, and then in a month, like 30 days, usually like 31 days, or February of 28 and 29, depends on whether they leap year or not. So 2/3 of the data is available, 1/3 we need to predict. So essentially we are going to predict it uh, for the next 10 days in a month, and then backtrack into back testing. We will see whether we have the prediction is good or not. Well, the two kinds of data is available: hourly data and daily data. So hourly data actually has 17,379 records, and for daily data it is 731 days. All right, so this is the data which is available, and this data is also, particularly this 2 years data, has been taken by one of the researcher at University of Porto in Portugal. So, and in fact, he has posted this uh, in a research paper, and also detailed, cleaned data is available. So I opted from there. This is the data characteristic, or so-called data dictionary, and the data is available on, like, what is the number of instance, date, seasons, like whether it is a spring, summer, fall, winter. Year data, like 0, then it is 2011. 1 is 2012. Month is 1 to 12 months, January to December. Hour is 0 to 24, means first hour to 24th hour, so whole day. And hourly is again 0, the same, 0 to 24 hour. And another information is whether that particular day is a holiday, like non-working day, or whether it is working day. So weekdays are Monday to Friday, and non-working day is nothing but Saturday, Sunday, and otherwise holiday as well. So holiday can be uh, from work day, and of course non-working days are holiday as well. So it depends, and for that verification, here is this website where we can go and check it. Since it has been done, so that has been part of the data as well. So the effort has been very much reduced. It is very clean data. The other information is about the weather. So weather is like, weather, how is the weather? So weather is like, is a categorical, whether it is a clear weather like sunny, or little cloudy or pleasant, I would call it. Third is light snow, thunderstorm, and kind of cool. And fourth is heavy rain, or heavy snowfall and all, and very foggy. Uh, so there is kind of four kind of weather categories. And then there is a temperature, and air temperature, nothing but feel like temperature, like whether it's due to wind gust, uh, normal temperature, and a temperature we feel. So that is another attribute. Hum is nothing but humidity, and wind speed is there, which is kind of normalized data, which you will see. And uh, and then there are two kinds of people who share or rent the bike. They are casual and registered. So casual is like you can go just as, and you are not registered. And someone, those who are registered, like they are paying some regular fee. And casuals are like one of the use, so one time user. Okay. And registered are like they are mm, paying some monthly fee or annual fee. So that's the case. Okay, so this is the data, and we will go and see the data quality. The data quality has been checked actually, and I loaded into Python the Jupyter notebook. And why I have chosen the technologies and all these are part of architectural design document. And if you are reviewing it, please go through that. And I have a detailed 8-page document there. Well, coming back to quality of the data, the quality of the data is, as I mentioned, there is no missing data here. It's quite good. And of course, there are there are a lot of variances here, extreme, like minimum value of the count. Like the count is nothing but a particular day or particular hour number of rentals. So one, and max is 977. So huge difference, right? So the variance would be very high. And since whether working day, all these doesn't make sense, because average and mean and other things doesn't make sense. Since this is numeric data, it has been kind of calculated, and that is what we will do. And data transformation, we will have to convert it to a categorical variable. All right. So now we come to the data wrangling part and ETL, data visualization. So here the data transformation, as I mentioned, we need to transform numeric data to categorical. So that has been done here, and this is quite obvious. What are the data would be categorical, like months and season which we have, and even weather patterns, that has been 4 categories. So all this has to be converted as a categorical variable. So whether it is working day or not, 0 or 1 binary in fact, and hour has been converted again category, like first hour, second hour, third hour, like this. So that has been converted. And only temperature, feel like temperature, humidity, wind speed are the float, and the registered or casual number of uh, users, since it has to be integer, so that is integer. And date and time, date time is nothing but a date time, so it is a special format, it is categorical. Well, so let's look at the missing data. As I in the earlier slide I showed, there is no missing data here, that the same has been kind of identified, since that is one of the criteria. So I have looked at, and also the overall data distribution. So of course we see there is kind of normality, but there's a left skewed. Okay, uh, and here, sorry, it's a right skew, and and there is no missing data. So now uh, some visual description of the data. So visual analytics here. Visual analytics, we are trying to visualize and understand the patterns. The legends has been given here for the sake of brevity. So 0 to 6 is 7 numbers which are kind of Sunday to Saturday, and weather patterns has been given. So sunny, clear, cloudy, misty, foggy, snowy, light, and fourth is rainy and heavy snowing. Uh, Another is spring, summer, fall, winter. Those are the seasons, and partly was the weather pattern. And if you look at the first chart here, rental over the weekend and weekdays. So this spike is nothing but actually over the period of time. So there are over a 24 hour, we see almost in the morning hour there is a peak, and again in the evening time there is a peak. It means office goers might be taking for the last mile drive. Okay, and these two, uh, which is pink, purple, or blue line, uh, are nothing but for weekends like Saturday and Sunday. You see that to office at the office hour, actually there is no peak actually. So for weekends there is a different pattern emerging here, right? So those are kind of leisure, those people going for leisure activities on weekends. And certainly in the evening it kind of lesser, and also uh, in the early morning it is very less. In the daytime on the weekdays uh, are less, but on the weekends the daytime is highest. So accordingly, so this is pretty much is emerging pattern, and it's quite obvious indeed. Let's look at the season here. So if you look at the season, uh, the season first is a spring. So so a spring is the blue, so that is high. So in the spring people have been riding bike a lot. But if you look at the fall, surprisingly green is fall, and very less people in the fall season. But then I believe fall people should be riding, because not very cold weather and it's pleasant. But one thing is here, summer is also good. So spring is good, and summer. So maybe summer is a little lower, because too much hot in summer when temperature rises, since it is kind of averaged out. So that time it may be lower. Okay, and again the pattern also over the time it also appears to be similar. where there is a peak hour, morning time, and evening time, again peak hour. And the peak is for bikers is very much in springtime, and also summertime. Okay, and look at the weather conditions. So in the weather, so we look at the blue legend is for sunny days, and while uh, the green is for foggiest lightest snow. So that is a really important observation here, that we see a pattern when the there's a light snow. So maybe people who are taking their, those who are not those commuting, they might be taking their for their last mile to quickly go to the places where they can either go to the subway or metro, or grab a public transport. So maybe those is the reason. That is what we speculate. All right, based on the what the data is telling us. How about the monthly pattern here? So again, in the monthly pattern, so it is a spread over January to December. So it's quite obvious the pink are those little cold weather time. So December, January, here Feb, and on the extreme left, January, Feb is lesser, and again in November, December is less. But if you look at March, April, it is has started building up. So May, June, July, August, September, and to extend October. So this has been kind of consistently high demand. Okay, quite obvious. That is the pleasant time for Washington DC climatic condition. And for, while if we look at weekly aggregation, it seems almost similar, except Saturday and Sunday is lesser, and Thursday and Friday is a significant, not so significant, but yeah, a little higher uh, is the demand. Okay, whatever the demand is here. So, but the weekly average is almost similar. Okay, that's a nice things to note. Okay, next one, let's understand some exploratory data analysis. Since we look at the data, how does the data look like? So there are extreme values and how that data distribution looks like. So it looks like where the total, the first is a box plot where look at, so less than 200, close to 170, 80 has been the mean, a median. And if you look at a lot of data beyond 600 are outlier. So the obvious range is from uh, something within this range. And for season, uh, as we observed here, a spring, and for a spring actually, so you see the lot of, this is the first one is a spring, and a lot of people, a lot of data, those who are uh, kind of casual, due to them there may be a lot of outliers because those are casual, not the registered ones, and in fact overall is less here. So it, and this is now here the pattern emerged. So blue, green is consistently high, uh, median on average is high for that is uh, the green third one is uh, fall. So I was surprised earlier, but here it pretty much emerges. Where if we discard the outliers, so if we discard the outlier values, so spring is the best time for biking. Okay, pretty much that's emerges. So it's this, and so mm, winter is 4, so that is so, but here it is for a spring, uh, heavily it is distorted, this data because of those casual uh, rider. And how the distribution is over the hours, of course we see here they are consistent, so that there is hardly any outlier, very uh, in the morning hour from morning 6 to 9, and again in the evening close to 4 p.m. to 7 p.m., or I would say 5 to 7, that would be better, and here 7 to 8. So if you like, there is a peak time in the morning and in the evening, and daytime there are a lot of here outliers. Okay, so this is consistent. Maybe those who are registered, they might be taking the last mile drive. And how the it fares in temperature. So the temperature has been kind of captured of those places, and how that and it has been captured for daily and monthly temperature. So look at the temperature and how it is changing, and so that is quite obvious. As the temperature is rising, uh, there is an increase in bikes average riding, but it also goes a little down when the temperature is becoming very high. It means it is becoming a hot summer. That time there is a little decline or flatten. So maybe the reason because of those are the peak summer time. And for the weather, actually it is pretty, yes, for working and non-working days it is almost same, because of those people who are going for leisure and those who are not. So whether it is a working day or holiday, and based on that it is coming. But of course for uh, non-working days, the data, if you look at how, whether we have, so non-working days, one is holiday, zero is otherwise is means working day. So one is working day. If day is neither weekend or holiday, means it is working days one, otherwise zero. So in the sense, one is higher when people are going for working day, that is higher, and in the outliers are also higher, like those who are taking uh, the, the ride. Now let's look at the correlation plot. So correlation actually suggests there are few variables which is kind of quite highly correlated, and for the sake of dimensionality reduction, though there are not much dimensions here, only 15 variables, and so the six variables were kind of consistent. So three were dropped and three were retained, and those three are here. So we dropped it like a temperature, casual, register. Why? Because we are predicting total number of, irrespective of. So the idea is that irrespective of whether person is a casual rider or registered rider, person is taking a bike from a certain place, renting a bike from a certain place, it means the total bike demand is important. So for that, we want to remove it. And temperature and feel like temperature are just a kind of highly correlated, and it's a linear transformation. So you know that it's linear dependent, so we need to remove it. Otherwise, it doesn't make sense. In fact, one is important to explain the other. So we retain the temperature, actual temperature, rather than feel like temperature. And feel like temperature has been dropped, and that is one of the feature engineering. Then we kind of did, and after that we did feature importance, and the feature importance here, it turns out that 12 number, that is of course count, and then that is our number which we are looking at, and these variables are here in descending order. And as per the feature importance, look at here what are the important variables. Okay, uh, one hot encoding we need to do, because we have transformed the data into categorical. Since when we are going to do make a model on the categorical data, we cannot do any uh, computations. So we need to do one hot encoding, like if those values are there, so we need to transform into vector, and that is what has been done. And after doing, eventually we get to uh, get 60 number of variables. So data increases huge. Now it is a huge data. Now modeling. So we will be using machine learning and deep learning. Let's go with the machine learning, and the particular technique is random forest. I've used several, and some in R actually, not in Python, and earlier. So I would like to take only one example here of random forest. And in the random forest has been used uh, an estimator, the like number of decision tree has been taken 350. They have taken 350, and a cross validation is 10. And with a replacement, that is bootstrap is by default true, and the accuracy of the result is this. So mean accuracy is 83.62%, close to mean absolute error. So like a mean absolute error from is nothing but like predicted minus actual, or actual minus predicted is absolute value actually. So sometimes can be negative, positive based on that whether we have predicted higher or lower than actual. So this table in the left in the chart, it shows the error. So this is nothing but the absolute error, and that if you take the average of this is nothing but this one. It comes around 46.53. So not bad actually. If we look at the 40, the mean is 170, 180, and the numbers goes up to 600, and if you uh, discard those outliers, which goes up to 977, as we saw, 1000, but what the number varies in between up to 600. So this is less than 10% in that sense, and in fact to 6 or 8%. So 8% variation to that range for the maximum value, I think is pretty good, but average is 46. When there is a less number, that is really difficult prediction. Let's say somewhere predicted value is 4, 12 was, and actual was only 4, so the difference is huge. But given that it is a root mean squared log error, so log error is nothing, we need to take it because there is a huge number, so we wanted to take a log, and the log error is coming less than 1. So it's okay, it's also good, and it's not bad for this kind of a lot of other factors. Since this kind of factor, and that I will discuss in my conclusion. So let's conclude here. So this is a scatter plot, and is so pretty much a linear. So the actual and of course a lot of data, a lot of points are in the middle. So essentially, if we are perfect, there will be only one line, and all the points should follow one line. But if you look at very closely, little fluctuation is a linearly, and there is a linear relationship is emerging very beautifully. So it means what the model has been able to predict is well, and of course there are some extreme values. As we know, there have been kind of extreme values, but considerably all the numbers are here in this range. Okay, uh, what I did here, what are the numbers, I kind of bucketize that into like 0, 200, less 200, 400, and color coded to see where the largest chunk are. So actually, those with a very less error, less than 200, and these are here actually. And if you see the color code is higher, means the higher the error, the absolute error. Actually, we are talking about the absolute error. This error is very lesser, right? Maximum is very less. It means the color code. So that color coding is telling us that actually the large number of the data have very less number of absolute error. It means we are pretty close in explaining it and or predicting it. And the extreme values are very fewer. If you discard them, then it's going to be very good model. So that is what we need to do, and discard those outliers, which we have not done it well. And so accuracy is 83.62%, and the meter is 45, not 45, close to 45, 46 actually. And what I suggest here, we look at that we have we need some geocode data so that it will be better to predict. That is not available since we looked at only Washington DC as central district area, and but uh, let's say other places are there, and also some other, like combining them with some telecom or some other sort of data, then it becomes easier. Why? Because we need to measure it from footfall, how the people density are there. So that's the reason we want to kind of factor that to understand, and may not be absolute number, but sometimes like whether is a less less number of people, crowded, much not very crowded, or those kind of categorical variable that may add some extra uh, insight and may help. Well, but with this data, we'll look at some deep learning model, neural network model. So here one of the deep learning model is like deep learning model where we have got a lot of hidden layers in between. So what I'm going to do, a neural network model, simplistic one with the back propagation, of course. And this is what the deep learning model is, where an input layer, then a hidden layer, and then one output. So what are the hyperparameters? Hyperparameters, number of iterations. I set it 5,000. Well, we can set it more, but since I was running into a learning rate zero point 0.4, not very less, not very high. You wanted to converge faster, and here if you choose very less, then it will take a lot of time to converge, but also there would be error because we wanted to ensure it should not be trapped in a. So those who are familiar with so that is uh, uh, stochastic gradient method has been used as a backprop actually. So it is a kind of optimization. And so how well the convergence is, the model training is, can we identify the loss function here on the training and validation set. So on training set it has converges, and validation set it has converges faster with a little time here. I think it can so it can converge even more on the validation set, or maybe some on training set we need to kind of do. So either more iterations or maybe a couple of more layer, so more number of parameters, so hyperparameters. And number of hidden nodes were 10 here, of course, and that is why it's in the model. And let's look at uh, uh, the predicted and actual. So this one is actual. Well, it has been kind of taken for a particular time, 2011 to 2000, uh, January 2011 till January 2011 here. And this one is not the same time. I'll just kind of want to see how the demands and how the actual data is varying. If you look at if you look at uh, the data for December, so actual data is orange line and blue line is predicted one. So this is very good, but as we kind of go for so we know we are predicting from till 21st, we have the data and we are predicting after 21 to 30th. So next 10 days we are predicting. First 20 days with data we are keeping, and next 10 days we are predicting. So there is a kind of a variations, more a spike, more variations on those predictions time. And when we check it, actually there has been some error that can be improvised, and that is what we. But it is good. Still, we are able to capture the demand and those spikes, the nature of the demands. We are able to capture. That is a beautiful thing here, as we see. It's just that little more variance is here, but we are able to capture the trend, and that is a good thing. So it's a fairly good prediction for today, and what we need to do is a kind of maybe one aspect would be part of its engineering, that we create multiple models. multiple model, like in random forest and traditional machine learning we did, but we averaged it out. But here we need to create different models for different uh, mm, specific season or 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 weather pattern. For that, it will help better accuracy because it won't average out, and it will capture the those nuances of those variations. Well, there is one more, like recurrent neural network or long short-term memory based, which is because it's a time series based and space and time. So that can be the back feed, not only feed forward, backward as feedback loop should be there. That would help us in improvising the solution. That would be the next. But for the time being, this is all from me, Kumar Hemant, and signing off. And you can contact me at the GitHub here and on LinkedIn. And this presentation is hosted at github.com//kmanta. And this is the IBM Advanced Data Science Capstone project presentation. Thank you for listening.